Okay, class, we're going to take a look at an example today of the inverse sine function and its use for an application. So right here I have a formula that says d of t equals 8 plus 3 times the sine of 0.5t. It has no meaning, right? So we're going to give it some meaning. What I'm going to tell you is that this is representing the depth of water in a harbor for any time t that's represented in hours. So that's helpful. And then we can start analyzing things. If this is depth of water, we can then talk about the maximum value the water reaches, the minimum value the water reaches, the average height the water is. We can talk about how long the period is, how long it takes to go through a full cycle. All those things come from this. So let's begin that process first by examining all of our pieces. Let's first remember that this 3 right here is the amplitude of the wave. If we were talking about a Ferris wheel, we could go back to say that that's equal to the radius. Since we're going to talk about this one in terms of depth of water, it doesn't make sense to call it a radius. It's the amplitude of the wave. So amplitude is 3. This number right here, it's the midline, so it's also the average height. Okay, so we have an average height, and we have the amplitude. Therefore, we can find when we're at a maximum height or a maximum depth. The maximum depth will be reached when the average height is added to the amplitude. Amplitude gives us the height above and the height below the average height. So this maximum value would then occur at an 8 plus 3, or 11. Let's give this a unit as well. Let's call this feet. So this will be the feet, the depth in feet in a harbor. So we could say that we'd reach a maximum depth of 11 feet. We could then look at a minimum value, and the minimum value would take the average line, the average being the 8, and subtract off the amplitude, do 8 minus 3, and that will give us a value of 5 feet. Well, the application of the inverse sine, the whole reason that we study inverse sine is to solve this algebraically to say things like, when will the height be at a depth of this or a depth of that? And so why might I ask you a question like this that will say, when, time-wise, will the depth reach a maximum depth of 11 feet? To write an expression for that, I would say something like 11 equals 8 plus 3 sine of 0.5t. And when I solve this, I'll be finding the time, the t value, for which I reach this depth of 11 feet. The water in the harbor reaches that depth. So we're going to solve this, again, algebraically. We would start by subtracting this 8. 11 subtract 8 here is going to leave 3. 3 will equal 3 sine of 0.5t. The next step would be to divide by 3. And that's going to leave a value of 1 equals the sine of 0.5t. Okay, so I move my solution to the top here. To solve for t, I'm going to need to undo the sign that I see. So it involves using an inverse. And here's where inverse comes in. Say the inverse sine of 1, and we apply the inverse sign on this side of the equation, the equal sign. And what happens is the inverse sign and the sign will cancel out, leaving out 0.5t, equivalent to the inverse sign of 1. Well, we're going to take the inverse sign, but we're going to do that in radian mode. The reason we choose radian mode is the radians are really measured in a unit that can be represented through time or length, more easily accessible than using degrees. So if I were to use my calculator on this, do inverse sine of 1, I'd find I'd get a number like 1.57. Now that's in radian measurements. So the inverse sine of 1 is actually pi over 2. Okay? So I'm going to leave it like this in terms of decimals, though, because it makes, I think, more sense to say this is about 1.5 or 1.6 hours than it does to say this is pi over 2 hours. All right? So I'm not quite finished with my expression, though. I need to still solve this for t. So I'll do this by dividing by a 0.5 here and dividing by a 0.5 here. Dividing by a half is the same as multiplying by 2. So this expression is going to turn into 3.14 is equivalent to t, which, as you know, is pi, our approximation of pi. So it's going to take about 3.1/10 of an hour to reach this maximum depth of 11 feet. Okay, well, then that's a good thing to know. The next thing I might want to know is, when will this occur again? When will I be at this depth again? Well, that's dependent upon the period of the function. So we're going to go back to the original expression. We didn't use anything with this yet. Right? Well, that 0.5 is known as the angular velocity. Well, in terms of the wave, it's going to be talking about a certain radian per time that we're dealing with. That's going to control how quickly the wave comes in and out. So this value right here, if I recall from our general sinusoid discussions we had in our last unit, we know that the period of this function would read 2 pi over 0.5, or equivalently, dividing by 0.5 as I multiply by 2, we have a period of 4 pi units. Okay? So the next time that I see this time occur, 3.14, would be one full cycle later. That might occur at a value of 3.14 plus a value of 4 pi. And that would again be in time. But let's not get too hasty. It might occur before then too. Remember what the sine function does. It's a full wave. There's some symmetry involved. So let's do a quick sketch here. Just a quick sketch of the symmetry here. If this is 0, this graph right here I know has been shifted up 8 units from the 0. 2, 3, 4, 5, 6, 7, 8. And then it's going to go 3 above and 3 below. 9, 10, 11. So I know a graph is going to do something like this. Right? And it'll keep repeating itself. And I'm telling you right now that this period from there to there, that's going to be the 4 pi piece we're talking about. So this would have to be at 8 pi. And this next value would be at 12 pi. So each of those values goes in that way. And then we'd reach a minimum right here at the 5. And we reach the maximum at 11. So as a quick sketch of this, we were interested in when we reach 11 feet. So 11 feet was the maximum value that was here. And then the next value that occurs is there. The next value that occurs is there. The next time it occurs will be the maximum. So in this particular scenario, we're starting at a maximum, and we're going to the next maximum, which is a full cycle later. The reason I wanted to sketch that, though, is sometimes I'm not interested in the max and min points. Sometimes I'm interested in something that's in between there. If I had said something about this equivalent to, say, 10 feet, I could have drawn an expression that looks something like this. And the graph would have had multiple intersection points. In fact, an infinite number of them have let the domain go large enough. But then on one cycle, I would have actually had 2 solutions, not just the one that I got for the maximum point. When that happens, then I've got to think more about the symmetry that occurs in here, that this second answer right here actually comes from taking the difference between half the period and subtracting off the value that was equivalent over here, the symmetry. So this value we would have gotten by doing the solution to setting this equal to 10. That same distance is the same distance from half a period this way. That's a little more complicated than I want to get with this problem. Stay tuned for more on that. But this particular solution comes out to be 3.14 for the time for a maximum height. And that would occur again one cycle later. But that cycle is determined by this value here.